All right. Hi, guys, and welcome back to Geology 106. We're here a little bit early, but we are not starting until 3 p.m. So I will just be here waiting for people to hop on and join our live classroom. Okay. All right, and I will be right back. Seems like we haven't had anyone join yet, so I'm just going to go grab a couple quick things. All right, looks like a few of you guys are here. If you want to say hello in the chat, go right ahead. Still got a few minutes before we start class, but yeah, welcome guys so far. Those of you who are here, back to our virtual classroom, also known as my kitchen for the time being. I'm working on getting a second home office set up because I am not the only person working from home during this time. So I am in need of a second home office, which I never thought that I would need two home offices, but here we are. So see that Echo is here and it's joined. Hi, Echo. And Alicia's also here. Good afternoon to you too. So for the few of you who are here, I definitely highly recommend perhaps printing out the PowerPoint slide sheets or having those up in a separate tab or something, somewhere where you can see the pictures as well as a place where you can take notes for today's lecture. If you haven't turned in those focus questions yet, they will probably go over most, if not all, of the answers for that today during lecture. I realized I originally thought that I had the time set for turning those in at 3 p.m. today. However, I realized that it's actually set for just before midnight tonight, which is totally just fine. I'm going to leave it that way. And I'm thinking that I might leave it that way for the rest of the quarter, as opposed to setting it due at 3 o'clock. Not quite sure yet. I might change that though. I'll post an announcement though to make sure that you guys are aware of the changes. I also highly recommend too subscribing to getting notifications on your phone or on your email from Canvas whenever an announcement is posted. I'm not sure how to do that exactly. I think it's a little bit different. I think it's a bit different for the student end versus the instructor end, how to subscribe to that. Especially if you've downloaded, particularly I'm referring to the phone app, if you have the app on your phone. But if you have the app on your phone, if you have a smartphone, definitely recommend turning on notifications for that. And if you don't have the app on a smartphone, or you don't have a smartphone, there is a way, I believe, to send notifications to your personal email if you don't use your student email very often. I also too can recommend if you don't like logging into your student email in addition to your personal email, you can set up forwards so that anything that's sent to your student email just gets forwarded to your personal email address. And then you don't have to be checking like 2 different emails. Let's see, Alicia says incentivize lecture participation. Yeah, I definitely think that. I think you're referring to the focus questions, kind of incentivizing participation during the lectures. Yeah, that's kind of partially the goal. Yeah, confirmation there. And then also we're going to be, for some of these chapters, doing things together during the lecture. So I'll mention this at the end of lecture today, but next week on Monday, we're actually going to be doing some things together during the live lecture with your rock kits. So there's some materials that you'll want to have on hand, including the rock kit, as well as just a few household items that will help with that as well. And I'm trying to think of more ways too throughout the quarter that I can incorporate little things that we can do during the live lectures with household items, just to kind of help get the visualization, because geology is definitely a very visual topic, and it's a challenge to teach it online for sure. Because normally with geology, I love to take students outside on at least one field trip. Our field trip, by the way, is canceled until further notice. If like the school allows me and the stay-at-home order is lifted, etc., and it's safe towards the end of the quarter to go outside and to travel together, I would definitely consider doing an optional field trip. Are there people who are still interested in perhaps doing an optional field trip if it's safe towards the end of the quarter? Let me know in the chat. All right, so Genesis and Echo are interested. I've also thought too about maybe doing something that is a bit more local, where people can, Avi says maybe, and Aveline says yes. I've also thought about maybe doing something a little bit more local, not sure where we would go towards the end of the quarter if it's safe, where people can all drive to the location. It's not far from, Everett or the greater Seattle area where we're all kind of located. I know Mount St. Helens is quite the jog. And that's probably not a drive that people would want to make. But if it's more local, perhaps it's the kind of drive that people are willing to make, and then everyone can just meet there. That way we're not traveling all in the same car, like breathing the same air. Does that sound like something that people might be interested in? Perhaps. Let's see. I think there's definitely a lag from when like chat messages show up on YouTube live streams. Resounding yes from Genesis there. Just looking over my lecture notes. Okay, so it looks like we have a few of you guys here for the start of lecture. Hopefully we get a few more people tuning in a little bit late. But today we're going to continue our talk about plate tectonics. So last Monday, or on Monday, we talked about plate tectonics, the idea, the theory, this really crazy theory that I know the first time I heard about it, it blew my mind. I don't know if it, is kind of like mind-boggling to any of you guys, but certainly was to me. I think, had anyone ever noticed before the continents, the edge of the continents kind of looking similar? Let me pull up my whiteboard here. How the shape of the North and South American continent kind of looks like, continents look kind of like the shape of the coastline of Europe and Africa. Anybody else ever noticed that? I mean, it was weird, and I feel like I might have noticed it when I was younger, but it was pointed out to me in 6th grade by my history instructor, our class. Pointed out hey, have you guys ever noticed this? Well, there are people who once think that the continents were all together in just one giant supermass. And that idea just rocked my world. I was like, what? How in the heck do you get, how have they moved apart? They were once together. Well, how is it that they look the way that they do today if they were once together? How do they, get across? Noah's ahead of the game, Pangea. It's not uncommon to see geologists with t-shirts or bumper stickers that say reunite Pangea. Pangea was the name of the supercontinent when all the continents, one of the supercontinents, when all the continents were joined together. So it's, not too uncommon to see people with kind of that cheesy joke that's reunite Pangea. We can do it, guys. Let's bring it back together. So let's go ahead, though, and continue with talking about Alfred Wegener really quickly, who's, again, he was considered to be the kind of the father of this idea. Less ocean travel, faster shipping. Yeah, I like it. So Alfred Wegener, who kind of really started playing with this idea and started being a really loud mouthpiece for it, I guess. One of the things that he was thinking about in regards to the continents being together, people were like, that's crazy. Sure, the edges of those, continents kind of look similar, but I mean, it's got to be a coincidence. Surely they can't just move. And Wegener's idea was that the continents drift around. He didn't really know how that was possible, and he didn't have a mechanism to explain it, which he really got a lot of flack for, was the fact that he didn't have a mechanism to really, truly explain it. He also got a lot of flack for his idea because Wegener was, by study, what he studied was meteorology. He wasn't a geologist. And for that reason, he was kind of seen as more of like an outsider in the community. The geologic elites weren't as fond of, these really radical idea coming from this man. And so it was his idea of continental drift was met with great skepticism. And I think that we definitely should meet new ideas with skepticism, but I definitely think we shouldn't also be writing them off. We should say, that's interesting. Let's look into that some more, especially using what's called the scientific method. It's how one does science. And we're going to talk a bit more about that next week. I really wanted to start off with plate tectonics, though, on the first week. And there's enough content in plate tectonics that it would be difficult to also cover yet another topic, the scientific method. So next week, when we talk about minerals, we're also going to talk kind of on the side about the scientific method. So he was bringing up this really radical idea of continental drift, and he proposed at least one mechanism for how this might happen. He was thinking of kind of like icebreaker ships. Have you guys ever seen an icebreaker ship, perhaps on like maybe a documentary or something, up in like Antarctica, or perhaps usually in like around the North Pole? Since the North Pole is just a giant ice cap, it's just seawater, frozen seawater. And so these icebreaker ships, if you look at the slide with Alfred Wegener's picture and continental drift, there is this icebreaker ship here. And what happens is that the ship kind of will ride up and drive on top of the ice. And it'll be there, and it'll just continue pushing forward onto the ice until the ice beneath the ship breaks, and the ship falls back down into the water. And they've broken apart the ice so that they can continue moving forward and continue sailing forward. And Alfred Wegener's idea was similar to this, that the continents, as they drifted across, they would kind of ride up perhaps on the ocean floor and break it, and then continue slowly migrating that way. That was one idea that he had. It's an interesting idea, not the strongest idea, especially since we weren't able to look at the ocean floor at that time. We just didn't really know what was beneath those waters, and thus it was really difficult to have a peek into what might be happening down there and see if that could help explain perhaps the continents moving around, if indeed that was the case. However, in the 1940s through the 1960s, we developed technology that allowed us to finally map the ocean floor and peer down beneath those waters without actually having to go there. I believe that they started doing a lot of this for World War II. I heard, I haven't verified this, but I heard that they were mapping the seafloor actually to search for underwater submarines, enemy submarines during World War II. And essentially what they were doing was they were sailing across the oceans and sending down basically a sonar type of pinging sound, and then receiving it back and mapping the ocean floor that way. So they were really looking for subs, is my understanding. But as a result, they also ended up mapping like the ocean floor. And there were some really fascinating discoveries that came as a result of finally being able to see the ocean floor and the topography of the ocean floor, where are their high points and low points. So the main thing to note, if you look at the next slide that I've got for you guys there, is these dark lines, right? And we can see that there's a major dark line right in between Europe and Africa, and then North and South America. What that is a topographic high point like this, right? And it's right down the center of the Atlantic Ocean. And not only that, but the shape of that line mirrors the coasts as well. So, not only do we now have two matching coastlines opposite side of the Atlantic, we also have that shape reflected in a topographic high right down virtually the center of the Atlantic Ocean in between those two coastlines. So with the discovery of all of these, we call those mid-ocean ridges where there's that topographic high, because it's this kind of high ridge. And with the discovery of these mid-ocean ridges, we suddenly had a lot more confirmation for this idea that perhaps these continents were once together all along that ridge spot. And then we also have some other ridges too, which gave rise to the idea of more movement going on, right? Also the presence of volcanoes, volcanic activity in the locations where they are, in conjunction with earthquakes too, also gives support to the idea that there are these boundaries where the crust is indeed broken up and is either crashing against one another, pulling apart from each other, or sliding past each other. So, and we kind of looked at that analogy too of the hard-boiled egg, right? Where the broken shell of like a hard-boiled egg is pretty analogous to the idea of like the Earth's crust also being broken up into these plates. So let's go ahead, and I realize that I'm not as much of a fan of the original organization sequence that I had my slides in. So if you're following along with the slides, go ahead and turn over to the slides or scroll over to the slides that talk about types of plate boundaries, as well as evidence for plate motion. I'll actually go to this one first really quick. Hopefully you guys can kind of see on this map here, right here, that there are some arrows on that map that all point in different directions. We actually have GPS data that tracks the movement of the plates. So you can set up GPS monuments, global positioning, global positioning satellite. You can set up these monuments and you set an anchor point essentially somewhere else on the globe. And you can track the movement of these plates. I actually did a really, really cool class called Geodetics, where we went out and we did do this. We didn't do it with just the tectonic plate movement in general, because that takes a lot of time. They compare the movement of these plates from data that they've been collecting, for years. What we did though was we set up these GPS monuments on a volcano. If you guys have ever heard of the Three Sister volcanoes in Oregon, there's North Sister, South Sister, Middle Sister. We set up monuments on South Sister and then collected GPS data, compared that to data from years prior when GPS monuments had been set up, and you can actually see how the volcano has swelled, right, with activity within the volcano, or deflated. And it's that tracking of movement though that we're looking at with tectonic plates on that map, where you have all these arrows kind of going every which way. It's showing that the plate is actually moving in the direction that those arrows are pointing. The how long the arrows are shows how how fast the plate is moving. So if it's a larger arrow, it means that it's migrating in that direction at kind of a faster rate. The arrows, of course, are exaggerated, though. Plates don't usually move that fast. So yeah, I see that in the chat that the East African Rift Valley is one such place where the continents are pulling apart. In these slides, I have a link to a video. It's right here, East African Rift Valley. There's a link right here. You gotta watch it. It's crazy. Back in 2018, a fissure actually opened in the Earth's crust overnight. And it was quite large, and it actually broke up like, you know, a road that people were trying to go across, and they're like, oh, crud, you can't get to the other side now because this fissure opened up where the Earth's crust is literally coming apart. And there's a few places on the globe, on the Earth's like on land, where that's happening at a very slow rate. But yeah, check out that video because they show the footage of that rift. They don't actually show it pulling apart. Unfortunately, that happened like I think during the middle of the night, and who would have known to have a camera there anyways, like during the time that it happened. But it's pretty neat, and it happened 2 years ago in spring of 2018. So let's go ahead though and go back to that slide right before this one, where we're going to talk about the different types of plate boundaries. For right now, originally I would normally talk, or in the past I have talked about how the plates move, but I think that that's kind of putting the cart before the horse. So for now, just stick with me and accept that the plates move, and we'll go over the mechanisms for how those plates move, because I'm going to go over some terms that'll make a little bit more sense for when we actually start talking about the mechanisms that cause plate movement. So there are three main types of plate boundaries. However, there are some subcategories to the first two types of plate boundaries. Let me grab my whiteboard here so that I can start drawing some diagrams for you guys. So the first type that I will talk about, we've already been mentioning it here, are divergent plate boundaries. Areas where the crust is coming apart and pulling away from another portion of the Earth's crust. So that's called a divergent plate boundary. So in these areas, imagine that these two bars are the Earth's crust here, essentially floating above the Earth's mantle. And they are literally pulling apart from each other, right? So I will briefly mention too the other types of plate boundaries. So they are convergent and transform plate boundaries. It's important to note too, before I continue talking about these different types of plate boundaries, that there's two types of crust. The Earth's crust really has two main types, and they are a little bit different than each other. And that's going to factor into what happens at these plate boundaries at the margins of where the Earth's crust is broken up. So let's see, I'll use this side of the whiteboard. We'll rewrite those at a later time. So there's two types of Earth's crust. There's oceanic crust. Oops. And there is continental. Sorry if I spell stuff wrong. I have mild dyslexia. So hopefully I spell everything right. But it comes out wonderfully when my husband tries to get me to play Dance Dance Revolution with him. Yeah, it's a challenge. So we have two types of crust, though, oceanic and continental crust. It's really important to know the difference between the two. So oceanic crust, obviously, hence the name, it's underneath the ocean. Continental crust is the land masses, which make up the continents. Oceanic crust is made up of a certain type of rock, which we will start covering in 2 weeks from now. That rock is really dense. It's very heavy. And as a result, it kind of sits a little bit lower. It floats lower in the mantle, if you will, than the continental crust. The continental crust is a lot thicker. It is much thicker. However, it is significantly lighter in weight. It's kind of like, think of a lead weight in water versus a giant buoy in water. So oceanic crust is kind of like that lead weight. It's not very big. It's definitely really heavy, and it sinks more, right? If you were to put a lead weight on top of something like, say, my favorite analogy that I like to use for the mantle, since the mantle is solid, it's not liquid, it's solid, is a candle, specifically warm candle wax, not melted candle wax where it's completely liquid, but where it's just warm. And if you guys have ever played around with warm candle wax, it gets kind of like squishy and malleable, right? So that you can kind of like mold it while it's still warm. That's kind of how I like to think of the mantle. And if you were to put a lead weight on like warm, malleable candle wax, it would compress it quite a bit and it would kind of sink, right? Whereas if you have something like a large buoy in water, it's going to float just because it doesn't, its properties are such that it's not going to sink. And it's also convenient for this analogy, quite larger than, say, a lead weight. So you've got oceanic crust. It's smaller, but it's really dense. And it kind of sits a bit like this, on top of the mantle. It kind of makes a bit of a depression, right, where it sits. Continental crust, by contrast, let's get a different color here. A few different colors going, maybe. We use kind of a red here for the mantle, right? Continental crust, by contrast, is a lot thicker. Hopefully, can you guys see that? Yeah, I think it's in frame. Continental crust is a lot thicker than the oceanic crust, right? This plate boundary doesn't actually look like that. Sorry, guys. It's okay. We'll get there. We'll get there. So oceanic crust sits a lot higher, right? And sometimes there's not always a plate boundary right here. Sometimes you do have on the same cracked eggshell both types of crust, right? So the oceans are not the strict boundaries for where the edges of these cracked eggshells, if you will, are. So you might still have like this kind of thing going on. Probably sit up a lot higher though, because that is the nature of the game here, where this guy is going to be lower and this guy's going to be up higher, right? But it's a lot thicker. So that's going to be important when we start talking about certain types, the next type of plate boundary, the convergent type of plate boundary. So at divergent plate boundaries, it's fairly simple and fairly straightforward, though, whether it's continental crust, oceanic crust on both sides, continental on both sides, or whether it's, continental on one side and oceanic on the other. Essentially, the two plates are moving away from each other, and typically we get some mantle upwelling going on here, right? Because the mantle is like, oh, geez, thank goodness I don't have this tremendous weight on my shoulders anymore. I feel like free, like I can finally stand up straight, with my head high, and it does. And we get a lot of volcanic activity in these areas as a result of the mantle finally being under less pressure, right? So typically what happens, because this is at a slower rate and it's not like a catastrophic process where the earth just rips apart and all of a sudden we have miles and miles and you go straight down into the mantle. Typically what happens is you get this kind of rift forming right here. And this is what it's like on the East African rift, as well as Iceland. It's another place on land where the continents are coming apart. You get these volcanoes. That's supposed to be a volcano, right? So you get a lot of volcanic activity as a result, where melting of the mantle occurs. The mantle, when it has less pressure on it, it's like, oh, geez, I can finally breathe. And as a result of it breathing, it also melts stuff and becomes kind of liquidy, right? And then we start forming volcanoes. So this also happens underwater too. There are a lot of underwater volcanoes around mid-ocean ridges. Underwater volcanoes are really cool to study. If you're curious about learning more about underwater volcanoes, see, someone up at Western, I believe her name is Jackie. I'm sorry, Jackie. I forgot your name, Dr. Jackie. But there is a gal named Jackie in their geology department who her sole area of study is underwater volcanoes. So that's kind of divergent plate boundaries. Plates coming apart. Fairly simple. Right, so now let's talk about, that's divergent. Let's talk about convergent types of plate boundaries. I'm going to erase this part 2. So convergent plate boundaries are where the plates are actually colliding. So those eggshells, the edges of those eggshells are running into one another. So, but we talked about how we've got 2 types of crust, right? We've got our oceanic crust, denser but thinner. And we have continental crust, which is lighter but thicker. It's gonna be important, guys. So convergent plate boundaries, that's where you have the edges of plates that are coming together, right? What happens as a result, though, when the edges of 2 plates come together? What geologically happens? Well, there's a few things that happen, and it depends on what type of crust is coming together. Is the edge of that tectonic plate oceanic, or is the edge of that plate continental crust? It's going to, the different densities is going to a traumatic breakup. Traumatic breakups. Oh my gosh. No, not quite. It is traumatic, but breakup would be more for like the divergent plate boundaries. Here we've got a convergent, so the coming together, right? What happens if we have, let's see, which one should I go over first? Let me look at my notes here, kind of. For let's go over, looks like in the PowerPoint slides, I go over oceanic first. So let's talk about that one first. So when the edge of a tectonic plate is consists of oceanic crust and the leading edge of another continental plate, or excuse me, tectonic plate is oceanic. What happens as a result of these two guys, right, forming is that tectonic plates aren't completely uniform. One of these guys is going to be slightly different than the other. Perhaps this one's a bit thicker, right? Who knows? Essentially, when they crash into one another, because they're both really, really dense, one of these guys is going to win. One of these guys is going to lose. As they come together, due to the fact that they're heavy, they're kind of like lead weights, one of these guys is going to end up going beneath the other one, and the other one is going to ride up on top of the other one, right? That's supposed to be an arrow. That didn't turn out very well, though. So one of these is going to ride up above the other one. The other one is going to sink below the other one as they bump into one another and continue being pushed towards one another. And we call this subduction when one plate goes below another, when the edge of one plate goes beneath another plate edge. Subduction. So that's what happens when you have when the edges of two plates that are being pushed together are both oceanic crust on the edges of those plates. So this happens a lot. When this happens, we get some features such as volcanoes again as a result, because there's some interesting stuff that goes on here in this class. We don't go too deep. We like to, me and the other geology instructors on campus like to call this class the mile wide, inch deep class. So I won't go too much into the mechanisms of it, but this subduction does cause melting in the mantle. Did my red pen die here? I hope not. So this does cause some partial melting of the mantle. And as a result of that melting, that stuff's going to want to make its way up towards the surface of the earth, right? Let me move this arrow. And then we're going to get little volcanoes, right? It's not too uncommon for a line of volcanoes to form along that whole margin, those where the plates are being pushed together, the two ocean crust edges are being pushed together, and one is subducting below the other. So you can kind of see that in this diagram that is depicted right here on the slide. So we're in the ocean, right? And there are two giant eggshells. The edge of these two eggshells is depicted right here and right here. They're both oceanic crust, where we can see, this is the crust right here, the gray and the brown. We can see that it's thinner here, and it's thicker here, where we've got some continental crust going on, right? So this plate is the plate that's winning, and this one's the one that's losing. Sorry, guy. And it's subducting beneath this plate. And we can see, let me get a little closer in here. Sorry, the lighting's not that great. I'm hoping that in my, wherever I set up in my house, that I have a little bit better lighting. But we can see some partial melting going on here. And as this is the whole edge, right? Or at least part of the edge is being depicted here. And you can see some little dots here. Those are all volcanoes that are coming up. Only these volcanoes, can sometimes build on themselves and continue building up and building up until they're tall enough that they are above the surface of the ocean, and then they form an island, a volcanic island, right? Japan is one such island that sits on the plate boundary where the edge of the plates on either side are both oceanic plates. And it's created these volcanic islands, right? And we've got like Mount Fuji and stuff like that. So Japan is a really famous, we call these island arcs that form along the plate boundary. A lot of people ask me if Hawaii is one such island arc. It is not. It is related to plate tectonics, but it is not on the boundary of where the Earth is cracked. There's some different mechanisms that cause that, and we'll go over that at the end of lecture today. So how am I doing on time? I'm doing good on time. So earthquakes and volcanism is pretty common along these convergent plate boundaries, the oceanic convergent plate boundaries. And I think that that's probably all that I want to say about that. Let's see if there's any questions so far specifically about oceanic convergent or divergent plate boundaries. Go ahead and throw them in the chat, and I'll try and keep an eye on that and see if any of questions populate in there. So the next type, though, unless some questions start populating in there, the next type that we're going to talk about is oceanic continental. So what happens when two plates, these, eggshells, are coming together, and one of these plates, the edge of it is continental crust, this thicker, more lightweight, more buoyant stuff, meets oceanic crust. Well, let's talk about that. What do you guys think happens? Sound off in the chat with some predictions, perhaps, some hypotheses. Making sure I'm in frame there. All right. Oh, my red pen really is dying. I will get a new red pen. All right. So, what happens when we're coming together? So, did we get any hypotheses or questions? Continental slides above the oceanic due to density from Miss Alicia. Miss Alicia, you are actually exactly right. And it is because of the density differences. So, remember, lead weight, buoy right here. Imagine that, you had these two, a buoy and a lead weight being pushed together. The buoy is going to sit on top of the lead weight if you keep pushing the two items together, right? And it's because the lead weight is so much denser, than the buoy, right? Buoy's got a lot of mass. It's quite large. It's a big guy, but it's just not very, very heavy. It's not very dense. So we have these two guys coming together, and what happens when they finally crash together? Who's going to win? It's the continental plate. And then as these two continue to push towards one another, sometimes it's only one plate that's really doing most of the pushing than the other, but you can think of it either way. So as these two plates come together and continue marching on towards one another, this guy is going to sink below the edge of the other one. And we get some interesting geologic features as a result of this happening. Now, when you think oceanic continental plate boundaries, think of home sweet home. This is Washington right here. This is what we have going on off of our coast. When they talk about the big one, the earthquake, the big one going off, they're talking about a massive slip of this plate beneath the continental edge of our plate that is continental. That's an earthquake that's caused by a massive slip beneath here. That's also how Japan gets its massive earthquakes, right? Because you've got these two plates coming together. In their instance, they're both oceanic plates, right? But when there is like a really big slip that happens along that plate boundary, it releases a lot of energy, and that release of energy causes the shaking, and it creates those massively gigantic earthquakes. So when we talk about the big one here in Home Sweet Home, and maybe some of you guys have heard about people talking about the big one, we're probably here. We're a bit more inland. That's the mega earthquake that they're talking about. We have lots of little faults in the Earth's crust, and specifically on the edge of our continental crust. And there's some slip that happens along those cracks as well, and those cause smaller earthquakes. And that also kind of happens as a result, I believe, of some of the crunching that's happening as these two kind of come together. It definitely is, as Alicia said, it's a little traumatic, right? When these two, it's really more of a traumatic kind of crashing battle. When plates kind of come together, and leaves behind some scars as a result, right? So what do I want to do here? I'll actually show you guys the diagram that I've got here on the slide of the convergent plate boundaries for the oceanic continental. Hopefully you guys have the slide pulled up or out in front of you, printed, pulled up on a computer, whatever. This diagram here is actually of the Washington coast, kind of showing like we've got the Olympic Mountains and then the Cascade Mountains, right? And we see this plate boundary subducting below the other one, and we see some of that partial melting going on. Sorry guys, the lighting is so bad, but hopefully you all have your slides out and can see and follow along with me. What eventually happens too at when you have plates that are subducting beneath one another, this stuff right here, this leading edge, it eventually gets deep enough into the mantle. It's really hot down there. It's really hot down there. And it starts kind of making everything a little bit mushy, not necessarily completely melting. We're not necessarily in completely liquid territory here. But things start getting, at the very least, kind of malleable, right? And this gets reabsorbed into the mantle, right? And it just gets reincorporated into our mantle. So that's also important to note. In addition to the kind of partial melting, we're going to have to use black here, a black pen for our partial melting. So in addition to the partial, like a little bit of melting that goes on at the edges of these, the rest of it that keeps subducting down is going to get just reincorporated with the rest of the mantle, right? And again, mantle is like solid but mushy wax that's just been heated up. I can't tell you how many people get that wrong. You can give that test question, make that a test question. What is the mantle, liquid, solid, or gas? You can give that to a bunch of geology majors who are like at the end of getting their degree, and they'll still get it wrong. It's just so ingrained in a lot of people that the mantle is something other than solid, but it is solid. Think candle wax that's been warmed up and it's just squishy, and it can kind of move around because it's warm and squishy, right? And it's capable of being malleable. You can also think of that too as like when you heat up metal or like iron or something. So when you're like making, say, a blacksmith, like making a sword or something, they heat up the iron, right? And then they pound the iron into shape, right? It's capable of being malleable. So the last type of plate boundary, convergent plate boundaries that we have to go over is going to be continental. So the battle of the leading edges of when two plates are both continental. So any hypotheses maybe from you guys about what might happen in this case? This one's definitely like unique. This one's definitely kind of weird. It again happens as a result of the fact that both things aren't very dense. The red marker's not working. I'm just going to throw that over there. So I stop reaching for it. Use this for the mantle now. All right. Let's see. We get mountains, says Avi. Yes, we do. Awesome. So when these two keep marching on towards each other, or one of them's just being a jerk and keeps marching towards the other one and shoving it around, and it's like, hey, dude, why you gotta be like that, it ends up crumpling together and we get a mountain range here. So I have also an analogy for this as well, when the two crumple together and a mountain range gets created. Let's see if I'm able to set this up here on my kitchen table and angle my laptop's camera so that you guys are able to see this happen. All right. You guys can see my setup here with my box of markers and whatnot. So I've got these two tablecloths here, right? And these are going to be the edges of our tectonic plates, and the edges of these two plates are both continental crust. So what happens when these two come together, right, and they keep just marching on towards each other, is we get a nice little mountain range that forms. Because one's not denser than the other, they're both, and also they're not both really dense, they're both very light, right? They just keep crunching together. And this plate, the continental crust on this plate isn't as thick as the continental crust on this plate, so we've got some interesting folding that's going on, but essentially what happens is you get a mountain range that occurs where you have these two plates coming together. All right. So, all right. And then got my notes here. Anything else I need to say about that I'm kind of forgetting? We get these mountain belts that are built up. Get a little bit of partial melting there. I think that's all that I want to say about this. Is this also called transform? Asks Genesis. No, this is not transform. We are just about to talk about that, though, right now, what the word transform means. So that is a perfect question to segue us into the next thing that we are going to talk about. Thank you. Perfect timing. All right, we finally finished covering convergent plate boundaries. So we can now talk about the third type of plate boundary. So we've talked about where they come apart. We've talked about where they move towards each other and crash together. Now let's talk about what happens when they slide past one another. And that, my friends, is called a transform plate boundary. Any hypotheses about what kinds of activities or landforms may or may not form at these boundaries? Go ahead and sound off in the chat. Make some general ideas about what you think might happen to the Earth's crust as a result of the plates sliding past one another. Let's see. Make some notes, draw some pictures here. So let's go ahead and use the blue one. This one, I'm going to do it kind of in 3D a little bit. All right, so I have the edges of two plates. I happen to pick blue, so I guess that right now we are talking about continental edges. I should leave that guy kind of open because that's not the edge of the plate. Oops, wrong marker. Just kind of goes off, right? See if we got some hypotheses. Uneven sidewalks in California. Yes, we do get uneven sidewalks in California as a result. We get uneven fences too, and all kinds of shenanigans that make landowners go, crud, right? So essentially what we've got going on here is that one plate is moving one direction, the edge of one plate, and the edge of the other plate is moving in the opposite direction. Sometimes it's just one plate that's doing most of the moving and the other one's fairly stationary. And instead of going this way, sometimes it's the opposite direction, etc. Right? In all cases, it's still a transform plate boundary where they're sliding past one another. Typically, let's see, oh, did we get another theory? Depending on the rigidity and friction, we have a physicist here. I love it. Rigidity and friction between the plates, earthquakes, and minor shifting on land. Yes, we get a lot of earthquakes at these plate boundaries. We don't get a lot of partial melting occurring because we don't have plates subducting beneath one another. We don't have a lot of crashing going on between the two, causing some shenanigans there with pressures and whatnot. We just have two that are sliding past one another. So no partial melting really ends up going on here. We don't really get volcanoes at these plate boundaries like we do with the other types of plate boundaries. We really just get a lot of earthquakes. And this happens for whether it's two continental plates or whether it's, two oceanic plates, right, that are sliding past one another. Or if one of them is continental and one of them is oceanic, right? Same thing either way. We just get a lot of earthquakes. One plate doesn't go beneath the other because they really are just moving past one another. So yeah, they're pretty straightforward in that regard. They're kind of boring by comparison. We don't have a lot of complicated, well, it depends type of stuff going on, creating subtypes. like we do with convergent plate boundaries. So on the slide here, where it talks about transform boundaries, I have some photographs here. We have the San Andreas Fault, which is a very famous transform fault, and it's I'm not sure if it really qualifies as a plate boundary, but for this class, we're going to say that it qualifies as a plate boundary, so don't quote me on that. So you've got these two plates sliding past one another. You get some really interesting features that happen as a result. So here we have a fence that was built across, I believe this is also the San Andreas Fault. We have a fence that was built on that intersected it, and the fault slipped one day. The crack in the Earth's surface slipped one day. Part of it went one direction and part of it went the other, and their fence is no longer continuous. We also have some railroad tracks that are also along a transform crack in the ground. This is probably not a plate boundary, a crack that qualifies as the edge of one plate and or the edges of two plates. This is probably just a crack in the ground that doesn't go quite as deep. We call those cracks faults. You'll hear me use that term a lot, and we'll go over it when we talk more about earthquakes. So this is probably not the edges of some plates, but you get shenanigans that occur when you get that slip, right, along either side, if you've got stuff built on one side versus the other. So with that, all right, so we'll probably be here for a little bit longer today. Today's going to be a slightly longer lecture. Probably be here for another 15, 20 minutes. All right, so we just need to cover the mechanisms now of plate tectonics. What causes these plates to move around? Why do they move? Sure, we have them we've seen, that they, can run into each other, pull apart from each other, or slide along past one another. But why? Why? So what makes the plates shift? If you scroll back or turn back to this slide here, what makes the plates shift? I like the meme here. Do you even shift, bro? My brother's really into weightlifting. So what makes the plates shift? The first thing that we have that makes the plates shift any hypotheses? I mean, why? What the heck? Right? There's a few things that cause this to happen. The first one is going to be convection. Is convection. Now, what does that mean? Convection is the circulation of material. So essentially what we've got going on in the Earth is that we have a nice blue planet. Got the crust here, right? Got the mantle, and we've got the core, right? Can you guys see that? So we've got, the crust up here, this thin layer here. We've got the mantle here. We've got the core here, the inner and outer core. The core of our planet is very hot. It's very hot. It's hotter. It's the deeper you go, the hotter it gets, right? And this stuff, we said, is kind of like that squishy, warmed up wax, right? And the deeper you go in the mantle, right? If you're down close towards the core, it's really hot down there. Is it so hot that it melts the mantle? No, no. But this is where that whole like squishy bit comes in. It is hot enough and it is malleable enough that this area, as it is warmer than up here, right? So this part's a little chillier. This part here, down by the core, a little bit warmer. There's enough of a temperature difference that it also causes a density difference. And again, we're talking about like the buoy versus the lead weight. So this colder portion of the mantle is a little bit like heavier, it's colder. This is hotter, right? We think air circulation, hot air rises, you know, we think of the boiling water in your kitchen pan, right? You've got your water boiling here, right? So I'm so sad that my red pen died. Imagine this is fire for your burner here. If you've got a gas stove or perhaps you have an electric burner, whatever. The water towards the bottom of the pan, it's also hotter, right? Just like how we've got this really hot core. And what happens as a result? The hot water ends up rising because it's warmer. It's got a different density than the cold stuff. Well, as that stuff moves out of the way and up towards the surface of the water in your pot, the colder stuff sinks down to take its place. And you get this circulation, and that's the rolling boil, right? When you finally get your water to boil, and it creates that rolling boil where that water is really circulating. That's a liquid that's doing that, but something that's, you know, like the mantle that's solid and malleable can still do the same thing, and it does. So we get this circulation, right, where we have warmer mantle circulating, moving upwards, and we have colder mantle sinking down to take its place, right? So we currently believe, and we have the idea that it's this circulation of the mantle material upon which the crust sits, this broken pieces of crust sit, and then as the mantle circulates and moves around, it pulls with it the crust that's sitting on top of it with its circulation. So if this cold mantle is sinking, the idea is that it pulls that plate that's sitting on top of it along with it and ends up moving this plate kind of in that direction. Is that kind of making sense to people? Which in turn affects the crust. Yes, we have some hypotheses going on. Love it. Love it. In the chat there. So the plates aren't always like necessarily coming together. This circulation is probably very, you know, it's not uniform throughout our little sphere that we live on, and it causes things like stuff moving apart from each other in some areas. It causes stuff moving towards each other and sliding alongside each other. So that is one pretty good idea, pretty good theory for how the plates move around. Now, there are some other ideas that we have here. We've got two more big ideas that cause the plates on the surface of the mantle to move around and why that occurs. So if you look at the next slide of what makes the plates shift, we have slab pull. I love the fact that I don't have to worry about whether or not you guys have this stuff written down, because it's all recorded and you actually can go back and rewind the lecture and like get it written down later. So slab pull. This is the idea where you have that takes place along a convergent type of plate boundary, where you have either the edges of the plates are continental oceanic, or both edges of the plates are both oceanic crust. One of them, at least one of them, is that really dense type of crust that subducts back into the mantle, right? We need at least one of them. Let's talk about home sweet home, right? And we've got continental oceanic. Being pulled, we got this guy here. Subducting down pretty low. The idea of slab pull is that this dense crust, is so heavy and so dense that as it descends into the mantle, the sheer weight of it actually pulls itself down into the mantle. So yeah, that's basically the whole concept. Just the sheer weight of it pulls it down in beneath, right? And then I have a picture of a 2-year-old here, like throwing the blankets out of his crib. Isn't that so nice? I love children. But basically it serves as a decent analogy, and it was the best stock photo I could find, where if you have you guys ever been like sleeping during the night and you wake up and all the covers are like off of the bed and they're on the floor next to you? And you know you didn't throw them off. It's just the fact that one of the blankets is perhaps so heavy. I've got the wrong side of this on there. It's just the fact that it's so heavy that it pulls itself off, right? So it pulls itself off right like that. Gravity is kind of doing the work for it, just pulling that really heavy, very dense object down into the mantle. So that's the basic idea behind slab pull. Are you guys with me on that? Or is that kind of, let's see, which in turn affects the crust? Really cold. Let me go back and read Alicia's comments. I'm not sure if there's a question there or not. I'm not sure I fully understand your question as the blankets slide off the bed. So let's see. Considering the heat and shear size of the core and mantle, temperature gradients cause motion and bubbling in the mantle. I'm not so sure about bubbling necessarily, which in turn affects the crust, and really, really cold. I'm not sure that that's completely the idea. Really, the idea is just the fact that this really cold, dense object, right, is sitting on top of this warm, nice, warm mantle, and that cold, heavy object is indeed sinking in beneath it, just like when you have, and also due to, I assume, gravity as well. You know, you've got the edge of that blanket being, you know, the fact that most of the blanket or a large portion of the blanket is already off the bed just pulls itself further off the bed, right? That's just the worst when you wake up and you're like, I am freezing. And it's because your blankets have fallen off the bed. All right. So let's talk about the third reason why we believe that the plates shift. So, ridge push. So, this diagram here on this slide, this second diagram here, illustrates both slab pull and ridge push on it. Here we have the slab pull going on, and right here we have the ridge push. So let's draw that out together. So what ridge push is, let's go ahead and stick with the idea of both crust being oceanic. However, same thing if it's both continental or what have you. This idea of ridge push. So we are now talking about this occurs at the edge of plate boundaries that are divergent, where the plate boundaries, the edges of those plates are moving away from one another. So I'm going to erase this lower one here just so I have a bit more room to draw on the one above it, on the diagram above. Remember how I said that at the beginning of lecture, how the mantle suddenly is like, oh, wow, I feel like this tremendous weight has been lifted off of my shoulders. Thank goodness. I feel like a lot more free and like I can lift my head up high, you know, and it does so, right? And the mantle kind of gets a little bit closer to the Earth's surface, the surface of the crust, right? I'm still lamenting my red marker dyeing because I like to use red for the mantle so much more. What happens is the idea is that as this mantle is like, oh, thank goodness, I suddenly have this weight lifted off of my shoulders. I'm going to now rise up and migrate higher up, right? And away from the center of the earth. And I'm going to try to rise to the surface. The idea is that that rising actually helps further push the plates off to the side, right? This mantle trying to come up in between those plates actually further pushes them apart. And you have ridge push, right? RIP red marker, I know. That's okay, we'll get another one. And then you also have slab pull kind of occurring further down. I'm gonna use yet another marker because I don't want to get this arrow confused with plate, the overall plate motion direction. I have purple. We'll see if purple actually shows up as different than black though in this lighting. Barely. But essentially then further down the, further inwards of the tectonic plate, further in the eggshell, that this portion, the fact that it's not raised up a little bit where that mantle is coming up and pushing up, it's going to push the edges of these tectonic plates upwards. It's going to lift them up as it tries to also go upwards. And then as a result, just gravity is going to cause it to slide off and go this way. And again, we've got this nice heavy stuff over here that's just further kind of like pulling away, right? So yeah, this general idea of ridge push is the pushing up of this mantle material and causing it to the crust on top to kind of rise up a little bit and then just slide off onto either side. Are you guys with me so far? Let's see. Rockies, Andes, Cascades, Olympic. Altogether, make up the longest mountain range on Earth, says Noah. On land. On land. There is a bigger mountain range underneath the ocean. I will let you delve into that because you seem like someone who would probably hop on Google or Ecosia or your favorite search engine and you're like, excuse me, there's a longer mountain range? Yes, it is much longer. It's gigantic. Check it out. We'll probably end up talking about it, though, at some point. It's worth talking about today, though, actually. So that explains the three ideas for why the plates move. The last thing we need to talk about in the last 5 minutes is Hawaii and how Hawaii forms. This is going to be important for your lab because the lab is all about Hawaii, right? So we've got the surface of our planet here. I'm going to draw kind of a 3D here. This is the surface of the Earth. I don't know how I'm going to draw this. We're not doing a cross section. We're not looking inside the Earth. We're just looking at the surface of our beautiful blue planet. Right, and we've got Hawaii here. These nice, beautiful islands. Anyone been blessed enough to actually visit Hawaii? I have. My sister, poor thing, it was the only nursing school that she got into out of the ones she applied to was the one on Hawaii. So that's where she went to school, and I just had to visit her, you know, for moral support while she was there, all alone on that island. Away from her family, so had to go visit her. Let's actually take a look into the cross section of what's going on under the Earth's surface. I changed my mind. So now let's take a look at a side view. We'll cut into the Earth and take a look at what's happening. So we've got our crust here, perfectly drawn, no errors whatsoever. And we've got our mantle down here below, right? M for mantle. And essentially the idea behind Hawaii is not that it's the edges of these plates, these eggshells, if you will, continuing with that analogy. This is actually somewhere in the center-ish, or maybe kind of not quite centered, but it's within the tectonic plate. But in this mantle, for some reason, scientists are still working on trying to figure out perhaps why this is the case. But you just have a really, really hot portion of the mantle that is welling up. So just for some reason, there's a spot, and we call it that, in fact, a hot spot. There's a particular spot in the mantle that's just, you know, it's not quite so hot that it has become all the way through the mantle completely like liquid hot, but it is significantly so much warmer than the rest of the stuff around it that you get that convection going on, and it's moving a bit faster, quite a bit faster. And that towards the surface up here, towards the surface of the Earth, you do actually get some partial melting going on. So we do get some liquid stuff here. That liquid stuff, we call it magma. And it eventually melts the crust itself and can form, some nice little volcanoes here. They start out as underwater volcanoes in the case of Hawaii. However, if you have them on land mass, they form Yellowstone. But in the case of Hawaii, where it's out in the middle of the ocean, and on that tectonic plate where the mantle happens to be really hot, it first starts out as an underwater volcano that eventually keeps erupting. This mantle material just keeps coming, just keeps circulating and getting towards the surface, and it's super hot, and continues to erupt that material where it partially melts up at the surface, bringing up that new material to liquefy partially. Some of it liquefies, and it builds up this really tall volcano, eventually forming a large landmass that's an island, right? And we get Hawaii. Now, here's the idea. Even though we're not at the edge of a plate, the plate is still moving, right? But the idea here behind Hawaii is that the hot spot does not move, but the plate itself is moving across the top of that hot spot. And this process is still occurring.